Hi everyone. So in the previous video, we introduced the compartmental framework for the modeling of the infectious diseases and relation to the coronavirus pandemic. We explained the framework using models based on deterministic differential equations, and we are now going to explain their stochastic counterparts. And then in the next video, we will move to stochastic networks. You may know these as probabilistic social graphs or social networks. Just for the context, let's quickly recap the main differences between the stochastic and deterministic settings. And the deterministic models, the inflows and outflows of the different compartments are described by the differential equations. And once the initial conditions are specified, then we can solve the differential equations in implicit or explicit form for the various quantities of interest. And the stochastic approach, the flows are defined in probabilistic terms or via stochastic differential equations. Solving a stochastic model produces a stochastic process. So now we will only be able to answer questions in probabilistic terms. For example, once we have solved the deterministic system, we can tell what the number of infectives will be at each time. And the stochastic settings, which is more like real life, anything can happen. So we can only talk in terms of the probability distributions. Essentially, in the deterministic settings, one expects answers like the number of infectives in 2 weeks' time will be 10, no room for any doubt. Whereas in stochastic settings, one would be happy with the answer that there's a 95% probability that the number of infectives would be between 5 and 15. Usually, people would like to know just some summary measure of the distribution, say expected number of infectives over a certain time period or a percentile. Similarly, in the deterministic system, when the parameters and initial conditions are known, nothing is uncertain, so we would be able to tell whether the disease will become pandemic. And the stochastic settings, we have random processes as solutions, so such questions can't be answered for certainty. One can only hope to get the probabilities. Of course, the probability of outbreak will vary with the parameters of the problem. Same goes for other quantities of interest, such as duration of the epidemic and size of the epidemic. In summary then, there is a random element to the stochastic framework which increases the complexity, but one hopes that this added complexity will lead to more realistic description and hence better understanding of the dynamics of the disease. Now let's quickly recap the compartmental framework. We have the susceptibles compartment. These are the people who are susceptible to infection. The infected flows into the infective compartment. Under the SIS framework, the infectives upon recovery flow back into the susceptible compartment. This framework is for diseases where recovery doesn't provide long-term immunity, and as we mentioned before, this is usually the case for diseases caused by bacteria. In the SIR framework, the infectives flow into the removed compartment, which contains both people who have recovered with immunity to the virus or have died. This framework is for diseases where, upon recovery, one develops long-term immunity to the disease, and generally this is the case for virus-based infectious diseases. As we discussed, many variations are possible within the compartmental framework. For example, one can add more compartments such as exposed or add additional flows. We discussed how these two compartmental frameworks can be implemented using deterministic differential equations, and now we're gonna discuss their stochastic counterparts. Let's start with the SIS framework. Let's recall that we can view a stochastic process as a collection of random variables indexed by time. The time can be discrete or continuous, and the random variables here are the number of people in different compartments. The count of number of people is an integer, so our random variables are discrete, but if the size of the population is large, then we can treat these as continuous variables. Continuous variables are usually easier to handle analytically. So one can classify the stochastic approaches into 4 categories. A classic example of the discrete time discrete random variable is the chain binomial approach, where the number of infectives from one time point to the next are binomially distributed. This model is best for smaller populations such as a household. So if you have been quarantined in a household or a tiny block of apartments, then this is the model you should be using, but it becomes impractical for larger population. So we are not going to cover it here, but we might in a future video, given that it provides a very easy introduction to stochastic modeling. And this video we are going to discuss the continuous time models in the more general settings. By the way, here one deals with nonlinear equations, so even if you are not interested in epidemics, the maths is quite useful, and the models here bring the abstract concept to life and they become more relatable as a consequence. As before, we assume the total population is constant, so we are ignoring the births, deaths, and migrations, which is justified because epidemics usually last only a few months, so ignoring the vital dynamics is not going to make a huge difference. S and I are the random variables capturing the number of susceptibles and infectives respectively. As their sum is constant, we need to model just one of them, say I. Let the number of infectives at time t be I. Number of susceptibles would then be n minus I. Now the I is a stochastic process, so we should really be talking about probability of it taking the value I at time t. Now consider a small time step, delta t. We assume that the time step is so small that the process can change at most by 1. So a new person gets infected and I increases by 1. An infected person recovers and I reduces by 1, or no event happens. Now we consider the probability of I increasing by 1 during a small time interval of length delta t, conditional on the number of infectives at time t. We know this happens when an infective comes into a contact with the susceptible and infects the susceptible. We recall that the number of interactions between the susceptibles and the infectives will be of the scale s times I, and we represent the scaling factor by beta, which captures both the number of contacts and the probability of infections per unit time. So we can write the probability as follows. The O of delta t means the residual term will be of order delta t, which means it goes to 0 faster than delta t. Similarly, we can write the conditional probability of I decreasing by 1 unit, which happens when an infective recovers, which we assume happens at a rate proportional to the number of infectives, and we represent this rate per unit time by gamma. So the probability of this happening over a small interval will be gamma times I times the length of the interval. Again, the residual term will be of order delta t. And for the final node, we don't have to worry too much as the total probability equals 1, so it will be 1 minus the previous two probabilities. Now let's see it from the other side. Say we want to determine the probability that the value of I at time t plus delta t equals I. We can follow the logic we applied to the tree and reverse order. So it might be that there were I minus 1 infectives at time t, and one individual got infected during the small time interval, or there were I plus 1 infectives at time t and one of them recovered, or finally nothing happened during the small time interval. Now we need to change the conditional probabilities to reflect the new perspective. So for the first node, we just need to replace I by I minus 1. Let's abbreviate this term, and the analogous term in our new expression will just have I minus 1 in place of I. Let's note down this relationship for future reference, and let's move to the second node. We just have to replace I by I plus 1. And for consistency, let's also abbreviate this term. And let's note this relationship for generic I as well. And for the final node, we don't have to do anything, but let's abbreviate the terms in line with what we did to the previous equations. By the way, the probabilities take the simpler form because these are just probabilities of changes in the value of the process over an infinitesimal period. We know infinitesimal means infinitely small, and this is very much like retaining just the first term of the Taylor series expansion. So even for a nonlinear function, the first term in the Taylor expansion will provide sufficiently accurate estimate if the approximation interval is kept very small. Now to link the probabilities of the process values at time t plus delta t to the probabilities of the process values at time t, we just recall the Chapman-Kolmogorov equation. The combination of British and Russian names make it sound complicated, but all it's saying is the probability of infection increasing from some initial value at time 0 to I at time t plus delta t is equal to the probability of the number of infections going from the initial value at time 0 to some intermediate value at time t, and then from the intermediate value at time t to I at time t plus delta t, summed over all possible paths. As the time interval between the intermediate point and the final point is very small, which is our delta t, we only need to worry about the 3 possible paths in line with our 3 nodes tree. The probability of any other path over a small interval is negligible, or what we called order delta t. Now the standard way one writes this probability is as follows. It really is a succinct representation for the probability of the process taking value I at time t. We have 4 of them here, so let's replace them one by one. On the right hand side, they have the same t, but different values for I, this I minus 1, I plus 1, and I. And on the left hand side, we have I, but the time is t plus delta t. So let's make the replacements. Let's gather the O of delta t terms. The probabilities multiplied by order of delta t will give an expression of order delta t. So this is all legit. Now let's get rid of the big brackets. Now if we shift this p to the left hand side and divide through by delta t, and then let delta t goes to 0, the expression on the left hand side turns into a derivative and the last term becomes 0 because order of delta t term goes to 0 faster than delta t by definition. And just for convenience, let's rearrange the right hand side in order of increasing I. So what we got here is the Kolmogorov forward equation, or the Fokker Planck equation. In this case is a differential difference equation. Differential because we have the derivative term, and difference because we have the lagged and leading values of p. The equation is indexed by I, so it means it actually represents a system of differential difference equations. We know I, which is the number of infectives, could be any integer from 0 to n. So let's recite the sequence. If you plug in I equals to 0, then the first term on the right hand side will be 0 because the probability of negative number of infectives is 0, and the middle term will also be 0 because bi and di will be 0 when I is 0, and the last term we just replace I by 0. And if we plug in I equal to 1, then the first term will be 0 because b naught will give 0. For I equal to 2, we get full house. We just substitute 2 for I, and so on to n minus 1. For I equal to n, the b part of the second term will be 0 because bn will equal 0. And the last term will be 0 because the number of infectives can't be greater than n, which is the total size of the population. Now we can solve this system iteratively, starting with the initial number of infectives. However, the solution becomes tedious as the size increases, so one is better off using some numerical methods. Anyways, we have the equation for probabilities now, though in differential form, and once you have specified the probabilities, then you can do all cool things However, the calculations here will be slightly more involved compared to the situation where one can get a nice and easy analytical formula for the probability. Now, this system of equations can be easily represented in terms of matrices. As you can easily verify, the right-hand side can be written as the product of a matrix and a vector. So the differential equation in terms of matrices can be written as follows. And we recognize this equation as the Kolmogorov forward equation. The matrix Q is the infinitesimal generator. Solving this system for P will give you the probability distribution of the number of infectives at time t, and as we mentioned before, analytical expression is tedious, but numerical methods should be easy. Now, the discussion of probabilities won't be complete without discussion of the generating functions and characteristic functions. They give us a succinct summary of the probabilities, and here their importance is greater because the generating function can also be used to solve the differential difference equation, just like Laplace and Fourier transforms are used to solve differential equations in mathematics. We know the moment generating function as a function of a dummy variable, say theta, is defined as follows, where we can write the expectation as probability weighted sum. This is the same thing as the Laplace transform, but of a function which represents probability, and the probability generating function is given by this expression, which is similar to the Z transform in maths, and which again can be written as the probability weighted sum. And finally, the characteristic function is like Fourier transform. One can apply these transformations to the differential difference equation to deduce properties of the process such as mean, variance, or higher order moments, or to facilitate the solution of the equation. Let's quickly go through a few key steps of the moment generating function. We will skip detailed steps as the purpose is to get a rough idea, but if you're interested in the detailed steps, then we can cover it in a side video. We can multiply it through by the exponential term we see in the moment generating function. And if then sum over I, then the left hand side will become the derivative of the moment generating function with respect to t, and the right hand side, after some simplifications, the details of which we skip, becomes. So now you have a PDE for the moment generating function, which looks a lot easier than the previous equation, and you can try to solve the equation as an exercise, but we will just deduce the mean from this equation to allow for comparison with the deterministic case. Remember, when you take derivative of the moment generating function with respect to theta, and then set theta equal to 0, you get the first moment of the random variable, which is the expected value. As you can easily verify, if you differentiate the PDE for the moment generating function with respect to theta, and then set theta equal to 0, you will get this differential equation. So you can see the dependence on second moment, which means analytical solutions are harder to obtain. However, this equation is not strange to us. Remember, in the deterministic case, we saw that the number of infectives under the SIS are given by these differential equations. So it is the inflow from the susceptibles minus the outflows of the recovered. Now, if you rearrange this equation to separate the I and I squared terms, you see it's exactly the same equation except that expected value is replaced by the deterministic value. So the deterministic equation just kinda models the average of the stochastic process, which is easy to understand, but there is a subtle difference. Remember the basic inequality, which implies that the last term in our expected value differential equation will be greater than the corresponding term in the deterministic equation. Right, so this stochastic version of the SIS framework, in which we model the number of infectives as a discrete variable in continuous time, is quite easy to build and understand, but the numerical calculations for large population sizes are relatively involved, reason being the analytical solutions don't get prettier with size. But if the size is large, then one can pretend that the number of infectives is a continuous variable, so one can then get the nice stochastic differential equations. To get there, we have to do very little if we approach this through the limiting form of the forward equation. Now, if you look at the right-hand side of the equation, you see it looks like the numerator of the finite approximation of the second derivative. We are missing bits and bobs, but you can always add and subtract the missing terms. First, divide by 2 to balance the middle term. Now we added 1/2 of these terms, so we subtract 1/2 of these. And we only used 1/2 of these terms, so we need to add the remaining half. Now, as delta I is equal to 1, we can add the desired delta I terms in the denominators. Division by 1 doesn't make a difference, but it gives us the form that we want. Now let's combine the terms in the last line. Now let's pretend the number of infectives is a continuous variable which we represent by x. This should be a reasonable assumption for a larger population, by the way. Then delta I would become delta x. And we remember that in the diffusion processes, we write the probability as a function of x and t, as opposed to a function of t indexed by I. Similarly, the b will become a function of x, and the bi minus 1 will then be b of x minus delta x, because the step size is now delta x instead of delta I equal to 1, and analogously, bi plus 1 becomes. Same interpretation applies to the d's. If we make the replacements and then let delta x becomes very small, the left-hand side is easy. The first term on the right-hand side is just the finite difference approximation of the second derivative of the composite function b plus d times p. And the second term is the first derivative of the same function. And we have the continuous analog of the Kolmogorov forward equation, or what you might know as the Fokker Planck equation. Now remember, in the Fokker Planck equation video, we saw that if a process x is defined by the following SDE, then the Kolmogorov forward equation will be as follows. So here we need to go in the reverse direction. We have the Kolmogorov forward equation, and we would like to deduce the SDE, which is a very easy thing to do. The coefficient of p inside the first derivative is the drift, and the square of the coefficient of p inside the second derivative term is the diffusion coefficient. Now we can substitute the original parameters. We will have to replace I by x in the two equations first though, and then substitute these for b and d. So we have a diffusion SDE for the dynamics of the number of infectives, and we can do all cool things like simulate its paths, answer questions with Monte Carlo simulation, etc. If you are not comfortable with the diffusion, then you can also use jump processes, say Poisson. So you take the deterministic differential equation for the number of infectives and add a compensated Poisson process to allow for random changes in the number of infectives, and subtract another compensated Poisson process to allow for random changes in the number of recovered. So you have options. Now this was the SIS. Let's move to the SIR. Things are very similar but slightly complicated because we will have two random processes to deal with. This is because n is now sum of three variables, so we can reduce the system to 2 dimensions because n is constant, so knowing any two of the variables is enough. So we can follow the same process as before, but now we need to track both the number of susceptibles and the number of infectives, and we are now dealing with bivariate probability. Again, we consider a small interval so that only one type of event can happen in this short time interval. A susceptible gets infected, so S reduces by 1 and I increases by 1, or there is one recovery, so S stays the same and I reduces by 1, or neither an infection nor a recovery, so both variables remain unchanged. Now we can write the conditional probabilities as before, but we have to write these as function of two variables, S and I. the flow from S to I per unit time will then again be beta times the number of infectives times the number of susceptibles, and the residual will be of order delta t. The next one is same as in SIS, gamma times the number of infectives plus the order of delta t term. And then the last node is just 1 minus the previous two probabilities. We can link the probabilities of the process value at time t plus delta t and the process values at time t via the Chapman-Kolmogorov equation, which is now two-dimensional. We want to see the conditional probabilities from time t plus delta t perspective. So if the processes were to take values j and I at time t plus delta t, then we know that in the first node there would have been one infection. So the number of susceptibles at the previous observation would have been one higher and the number of infectives one lower. The second node represents recovery, so it means number of susceptibles won't have changed and the number of infectives would have been one higher, and the last node stays the same. So in the Chapman-Kolmogorov, only 3 combinations contribute to the sum. So we substitute j plus 1 for m and I minus 1 for n, then j for m and I plus 1 for n, and then just replace m and n by j and I. Now we can abbreviate the probability as before, except that here we have double indexation, j and I, so it represents the probability of the number of susceptibles and the number of infectives being equal to j and I respectively. We can substitute for the first conditional probability, which is just the probability of new infection, so it will be beta times number of susceptibles times number of infectives, and then abbreviate the probability term. We can then substitute for the conditional probability in the second line, which is just the probability of recovery, so gamma times number of infectives, and again abbreviate the probability. And finally, we substitute for the conditional probability in the third line, which is the probability of no change, and then abbreviate the probability and add the order of delta t term to capture the residual effects. Now, as in the SIS example, we can proceed by shifting p to the left-hand side, dividing through by delta t, and if we then let delta t goes to 0, we get the Kolmogorov forward equation for the SIR model, which is now two-dimensional as one would expect. And one can now calculate its moment generating and probability generating function, though everything will be two-dimensional now. And we can then also infer the continuous time analogues in the form of an SDE, which will now be a system of two SDEs. So everything is similar to the SIS but two-dimensional. We hope you enjoyed the video and we look forward to seeing you in the next, when we introduce the networks into the framework to get even more realistic description of the epidemic process.